Yeah, it should be working. Okay, so here's our notes today. This is a very theory-based lesson. We're actually not going to do any calculations today. I'm going to save the calculations for our next lesson. Um, I had originally planned on doing a quiz on Monday, but I changed the schedule. I flipped it around. Let's do one more lesson before we do our first quiz. So tomorrow I'm going to give you guys a work day, and then Monday we'll do topic 5, and then Tuesday we'll do our quiz. I think that'll help you guys if I just do one more lesson before we do it. Not that there's not stuff that's on the quiz that's from topic 5, but I think it'll help consolidate your learning. So, okay, anyways, here's our concept today, very terminology based lesson. It's a lot of lingo. We're going to discuss the definition of acids and bases, and it's all going to be based on the idea of proton transfer. Okay? I'm going to go back a slide here to what I was just working with here. When we were talking about hydrogens moving, what is H plus? Well, effectively it's a proton, right? Because isn't hydrogen would have one proton and it would have one electron. But if it's H plus, we've now lost the electron. So really, all we have is a proton. And I find that really cool is that this has major overlap with our electrochemistry. I think it's super cool how the way that our world apparently works is that we can take an entire unit and talk about oxidizing agents and reducing agents and Leo saying gur, and that was all about electrons moving. And that created batteries. And what we've now starting to discover is that acids and bases are actually based on the opposite of an electron. They're actually based on protons moving. If you have a hydrogen moving towards water, it makes it acidic. Say that again. You can think of this in your head. If you have a hydrogen moving towards water, it makes it acidic because the water now becomes H3O plus. If you have a proton moving out of water, it makes it basic because now your H2O just becomes HO negative, which is a base. And so that's why I think this is really cool. They're really similar to redox reactions. So we actually are going to have some new definitions here. From now on, an acid is going to be anyone who donates a proton. Because if you can give water that extra proton, then it can now become acidic. And a base is now known as a proton acceptor or a proton thief, almost the exact same way as we had in redox, where this guy right here is like, you know how in redox we have the one who gains electrons and loses electrons? This one right here is the one who has like the loss of protons is an acid. Doesn't really make it as good of an acronym, but if you lose a proton, you're an acid, right? Sometimes we write it like this, if you're HA, that's like a short definition for an acid, and you react it with water, if you can give your hydrogen away, you can make yourself some H3O+. That's an acid. So losing a proton makes you an acid. Accepting a proton then makes you a base. Sometimes we'll write this as like B negative for base. And if I were to react it with water, if it can, the negative portion of this guy right here, if it can steal the hydrogen away, it can make the OH minus. And so it's very similar to redox. We have gaining and losing. Only rather than gaining and losing electrons, we're now gaining and losing protons. And this kind of fundamentally changed the way that we talk about acids and bases. It doesn't actually change how acids and bases work because they've always worked the exact same way. But this idea didn't really happen until we discovered protons, neutrons, and electrons, right? I've talked to you guys about some of the history of chemistry and physics, right? Really, the groundbreaking experiment would have been in about 1908, Rutherford discovering the nucleus. I mean, the idea of even knowing about the nucleus and protons and neutrons and electrons, it's only just over 100 years old, right? So now we actually have the terminology just over 100. Did I say just under? Yeah, so it's like 100 or so years old, right? 110 years old right now, right? In terms of how long we've even known about nucleuses and electrons and protons in this way. And so I guess what I'm trying to get at here is that in the last, like this is fairly recent in terms of chemistry. Chemists have always known about acids and bases, but now we can describe them even better. We describe them not based on whether they have an H in their formula, but whether or not the hydrogen moves. If you lose a hydrogen, you're an acid. If you gain a hydrogen, you're a base. And that's kind of what I've got for some pictures right here. Okay, here's HCl, and you guys will recognize this because it's like the first acid you learn about back in grade 9 or grade 10, right? You were taught this is an acid, probably originally because it starts with an H. which, I mean, is fair enough. I can give you some examples, by the way, of things that start with H that actually aren't acids. But if it starts with an H, it's a good indicator. But here's the better reason why. This proton leaves the HCl. This was a loss of a proton makes you an acid. I don't actually have a good acronym for it, but this guy lost a proton. But hey, look, it produced an acid. Now, this kind of comes back together with our equilibrium unit in that there are some acids and some bases that they don't actually occur at equilibrium. They happen all the time. And the reason why is that, kind of like my thing from yesterday where I said that we are never ever getting back together, the Taylor Swift kind of idea here. There are some things where, like, when they react, they stay that way, they stay separated, it is done. And we call those things strong. Not because they're more dangerous, but they're considered strong because they never reform. When A turns into B, it stays that way. And there's only 6 known strong acids. They're the ones that are on your table. I have a slide of that sitting in here somewhere. You guys know this table right here? There are 6 known strong acids. I know it's blurry, but it's HClO4, HI, HBr, HCl, H2SO4, and HNO3. These are considered to be the 6 strongest acids because they don't reform. They stay broken up, basically. Everything else that's below that, though, can be written with an equilibrium expression. So when I try this one down here, NH3, and I add it to water, you guys have probably seen this one before. Water is going to lose its proton because this guy is a proton stealer. And what ends up happening here is it produces the OH minus and NH4 plus. But if it's not something that's considered strong, we write it with a double-sided arrow, because what ends up happening is this guy over here now has an extra proton. And what can actually happen is this guy can give his proton right back to this guy, reforming water. And what ends up happening is we have what's called acid-base conjugate pairs, where what ends up happening is this guy right here is a base because this acid right here kind of gives its proton away to it. But over here, I mean, this guy is a base because what ends up happening is this acid right here gives its proton back to it, causing the reverse reaction. So you actually have pairs of them. You have this guy giving his proton to him, becoming this guy, but then this guy gives his proton right back to here, causing it to become this guy, who then gives its proton to here. The analogy I use is it's kind of like a hot potato, where it's like, here's a hydrogen atom, here, take it. No, give it back, give it back, give it back. No, take it back, right? That's the equilibrium that's going on. You get what I'm saying there? And that's the hydrogen that's taking place there, is that in this example between me and Daniel, I don't care who was really who, but I had a proton, I gave it to him. He turned into this guy right here with an extra pen in his hands, a proton, and he gave it right back to me. And then I gave it back to him. He gave it back to me, and that's where the equilibrium comes in. So what we're going to talk about a lot today is these equations, and what we need to be able to do is label the base and the acid, but on both sides of the equations. So they're called acid-base conjugate pairs. So hence my next slide. So the basic concept here is that whenever you find substances that differ by only a proton, those are called your acid-base pairs. Can you guys actually stay on the slide we were just on, since I hear you guys flipping pages? I want to show you it on here. A lot of people will get this wrong on the diploma. They will say that these two things right here are the pairs. That's actually incorrect. These two things right here are not the pairs. The proper one, I'll try the highlighter here, is this. These two right here are pairs, and this one and this one are pairs. Okay, that's how we define them. The pairs are the ones that are on opposite sides of the equations, and they're the ones that differ by a proton. There's almost always a diploma question, and they'll make it like in like a 2-column kind of question. So I'll try to make one out for you here. It would look something like this. In the example above, which are the acid-base conjugate pairs? And they'd make it like A, B, C, D. And you know how sometimes they give you like an I and an I column, and they do two things? What they might do is they might say that an acid-base pair is NH3 with NH4, and they might do that twice. Or they might say that it's NH3 with water. They'll probably ask a different question for the other column here. What I guess I'm trying to say here is that these two things are not considered pairs with each other, but this one and this one, or this one and this one are. So this would be one of A or B, depending on what they ask you in those columns there. Does that make sense? So let me go back to some more pictures here if you guys now want to flip to the next slide here. This one's now got them kind of labeled. This is acetic acid, this is vinegar, and we've used this one before. The conjugate pair then is this thing right here, and once it loses its proton to here, that's the conjugate pair. Here it was an acid. Acids are things that lose protons. Who did this guy lose its proton to? Water. Because water is a base. Water likes to take protons. If you give away protons, you're an acid. If you take protons, you're a base. And it caused it to turn into these two things right here. But it didn't stay that way, because what happens is this acid right here gave its proton right back to this base here, just like my little silly hot potato game with Daniel there. Okay. And so I need you guys to be able to recognize acids and bases in the example here and label the conjugate ones. So this one and this one and this one and this one. Now, the data table, the page in your booklet that I've been showing you before, it actually will list for you, and it actually uses that terminology. It calls it a conjugate base. And so you'll be able to recognize that all of the things in these columns here, what is the only difference between column A and column B? There's one less hydrogen, right? This was HClO4, now it's just ClO4. This was HOOCCOOH, now it's HOOCCOO, no H. Where'd the H go? Yeah, probably to water to make H3O+. Yeah, which is why these guys are all acids, these guys are bases. Okay. Again, though, I really need to point out, though, the idea that this really only occurs because of our equilibrium sign. If you ever do have a strong acid and a strong base, and there's only 6, so like HCl plus water, for example, making H3O plus and Cl minus, we can probably still label you as an acid and you as a base, because really the proton went from acids to bases. That's also a good way of remembering things. You know how, like in the electrochemistry, electrons always went from anode to cathode? You guys recall that? Or hopefully you do. Electrons always went from anode to cathode. Protons always go from acids to bases. But if it's strong, there is no this guy giving his proton back to this one here. That wouldn't occur, because if it did, you'd put the double-sided arrow on. But the 6 strong ones don't. They're quantitative reactions. Okay. So, okay, so I've already kind of discussed our table a little bit. That's what this slide here talks about here. This table, the relative strengths of acids and bases, it's kind of like a redox table then as well. I've already discussed with you guys the idea that they're ranked according to their Ka value. And their Ka value, if you guys recall, is basically a way of measuring how much of the reaction proceeds before the equilibrium kind of reverses itself. But you can also approach the table in another way. These guys right here, up here, are the strongest of all the acids you have. Because these guys up here are the ones who want to get rid of protons. Like perchloric acid hates its proton. It really, no one wants to get rid of a proton more than perchloric acid. Because it really wants to just turn itself into its conjugate base and stay broken up. We are never getting back together. It's probably getting old by now. Whereas this one right here, this HSO4, does it want to get rid of its proton? Yeah. But is it willing to take it back in season 2? Sure. And you actually know the reason why I know that? The Ka value is less than 1, which means when I try to write this reaction out, I'll just have to write it over top here. Your HSO4, when it reacts with water, will turn into H3O plus and SO4 2 minus. But if this number right here is less than 1, it means that this reaction takes place less than half the time. So really, this stuff's going to turn into this stuff, but immediately it's going to start turning back again. Does that make sense? So does this guy here want to get rid of its proton? Yeah, maybe a little bit. So in terms of strength, really, In the similar way that we did this in our electrochem table, you can actually say these are your strongest acids going down. And funny enough, the way it works in your bases column is that down here, the lowest ones down here, these are considered your strongest bases going all the way up to the top. Very, very similar to your strongest oxidizing agent and your strongest reducing agent on your electrochem table. So if you have that table in front of you or somewhere nearby, what's the strongest base out there? Not on my table here, but on the full table. What's the strongest base on the full table? The lowest one down here on the side over here. OH minus. Doesn't actually make a lot of sense though. Isn't that what we originally taught you was a base? Anything with a hydroxide was a base. So if you could continue this table all the way down to the bottom, hydroxide is actually the strongest of all bases. Looks like they've got yogurt, muffins, cheese? Yep. Cheese? Pears. Plus, ooh, pears. Pears. And it looks like apples and oranges. Go grab some breakfast. All right, I'm going to move spots now. Let's see whether it works back here. So that it stays connected. Seems like it's working. I think so, yeah. Well, I wonder whether it's just that simple. Because, yeah, my old computer ran Windows 7, and the new one's running Windows 10, and I just wonder whether the operating system's able to somehow handle the program better. Because it lost connectivity all the time on my old computer. Seriously? Wow. Wow. Okay, so I guess most of what I'm trying to talk about today then is probably falls into one of two categories. One, I need to give you new terminology, what we call these things. The second thing is I really want to focus on how to use this table here. Because eventually, like our next lesson, I'm really going to focus again on how to use these Ka values. Before I get there, I want to make sure you kind of get the concept. So let me do one more quick review just because we got interrupted by lunch. Make sure it's clear here. So that I can erase everything. You can approach this table in one of two ways. The first way you can approach it is it's a ranking system based on these numbers for Ka. If you guys will recall, Ka basically tells you if you have a reaction where something is turning into this, but it's actually going to turn right back again, this tells you like what percentage you have. And so these guys right here are basically 100%. There's no equilibrium. These guys completely 100% change that way. Whereas this one right here might get maybe 50% of the way there. And these ones down here might get more like 30% of the way there. And by the time you get down to the bottom of the table, it might be like 0.1%. And so it tries to turn into products, but like immediately it goes back again. Right? So that's one way you can approach this table. But the second way you can approach this table is that these guys up here are strong acids. And by virtue of them being strong, what I mean is when they give away their proton and they break up, they don't return. Whereas here, this oxalic acid, it'll give away its proton, turn into this conjugate base, but then shortly later, it decides to actually rejoin back together again. This one holds out for a little bit, whereas these guys down here, they don't hold out at all. So that's why we consider these to be strong. So really, like your weakest acid is actually at the bottom of this table. Actually, let's do that one. What's the lowest acid on this table here? Water. Can water act as an acid? Yeah. How often? 2 times in a billion. But water can be an acid. But like as soon as water breaks up into its acid and base properties, it immediately goes back again, right? It's so rare. Right? That same principle then, similar to like your strongest oxidizing agent and your strongest reducing agents on your other table, applies here. Your strongest base resides down here and goes all the way up to here to your weakest base. So this thing right here is actually the weakest base, ClO3 minus, or ClO4 minus, I think it is. And the reason why is that this guy right here does not want to get a proton back. This guy right here wanted to give its proton away, probably gave it away to water. So it gave it away to water. It formed this guy plus H3O plus. Well, this H3O plus is not giving its proton back to this guy to like go back the other way. So these guys right here do not want protons. And that's the terminology I want to work on today. Acids like to get rid of protons. Bases like to take protons. These guys all here, they are all bases. They could, in theory, take a proton. Why, in theory, could they take a proton? Because they're all negative. Yeah, in theory, they could all take a proton. They choose not to. Does that make sense? Can this guy right here take a proton? Yep, he's negative. Does he want to? Sure. Yeah, I guess. These guys down here, could they take a proton? Yep, and they're more likely to. So the strongest base of hydroxide would love to take another proton. Let me go back to some of the slides I skipped here then. I was right about here. Here's a notation I need you guys to be familiar with. Rather than knowing specifically what acid we're talking about, sometimes we'll write it like this, HA, which just means that we've got some acid that has a proton. It could be HCl. It could be HNO3. It could be HCOOH. I really don't care what it is. And it doesn't even have to be the hydrogen at the beginning of the atom, by the way. It could be a OOCCOOH, and it could be this hydrogen that's the one that's going to come off. But what I'm trying to get at here is you have something with an extra hydrogen. And that extra hydrogen goes to this guy over here, and it forms this guy, which would be called its conjugate base. Well, one more thing I can discuss then is just like we did in redox, when I go to this table right here, what happens if we're not only reacting things with water? Is it still working? Oh, it did finally turn off. Come on, work again. There we go. But what happens if something like here on the table reacts with something there on the table? What if we're not always reacting with water? We can react with water for sure. But what if we decide to have one of these guys react here? Well, this is very similar to spontaneity. Remember how in our first table, if it went in a downhill trajectory, it was spontaneous? Well, what that means for us here is if it goes in a downhill trajectory, it's going to be more than 50% of the time. It's going to happen often. Whereas, what if we had something like this acid right here react with this base up here? See how it's an uphill trajectory? Well, that means that it's going to react less than 50% of the time. And so there's a very similar concept where there's kind of a fight for a proton, just like there was fights for electrons. If the strong acid is higher up than the base, then it most of the time steals the proton. Don't forget though, it's still a hot potato, so it still goes back and forth, but most of the time it has the proton. Whereas if you have an uphill trajectory here, this guy here is going to try to steal this guy's proton. It's just not going to do it very effectively, but it'll still happen occasionally. So that's where there's a bit of a break from electrochem. In electrochem, it either happens or it doesn't. Here, it's more like it happens lots or it happens once in a while. That's kind of like the main idea. And so that's where I'm going to finish off our lesson is we're going to write out some equations using our data booklet here. And we're going to try to make a prediction as to whether or not it's going to be spontaneous, meaning a more than 50% equation, or non-spontaneous, which would be a less than 50%. So I've got some more pictures here along the way, just to kind of illustrate the idea. Think of it as a fight. What I've got here is an acid. I like this analogy here. There's an acid here, and there's a base right here. And really, the question is this water molecule right here strong enough to rip the hydrogen away from this truck right here? If it is, then it's a more than 50% reaction. Why don't we actually look this one up in our books? This is this is acetic acid in water. So if you guys want to find your data booklets, I'll try to erase all my mess off of here. Find where water is and find where acetic acid is. Water is actually on the table in 2 locations, and I don't even have the full table on here. But the water you're looking for is this one right here, because this is water acting as a base, trying to rip a proton off of somebody. And I only have half the table here. I'm fairly certain that acetic acid is right about here. It's like right below the page break. So, based on this, is acetic acid a very strong acid? Not really. Water is actually not a bad base, though, in terms of where it's at here, because the way this is going to work is that in comparison, will this water right here be able to steal this guy's proton once in a while? Yeah, but is it often? No. Which is why I think the number was about like 1.3% of the time. Right? So this guy right here tries to steal this guy's proton, and immediately it goes back the other way. Right? Whereas if it had been here to here, then it would have happened a lot more often. So why don't I find my last examples here? I'm just going to go find the very, very end here because I've talked about what I need to. I'll go back to the slides later. Let's try our word examples here. So I've got basically two questions for you. Let's say that we had sodium hydroxide and vinegar, which is acetic acid. Let's try to write out the predominant reaction and figure out whether reactants or products are favored. So here's where I'm going to begin. Let me write out sodium hydroxide. Now hang on. Sodium hydroxide, though, we started the class talking about this. Ionic or covalent? Which means that sodium hydroxide would dissociate into Na plus ions and OH minus ions. Which of those two is probably more useful to us in this scenario here? Yeah, the OH, because what is OH? A very strong base, in fact, right? Remember how on our table, I won't be able to put the table here for us, so just pretend this is the table. OH minus is like basically about as low as you can get. It is a very, very strong base. Okay, now let's write out the acetic acid. So vinegar is CH3COOH. Now, it was in water, so I can also consider that as well. I consider that it could react with water. And if it was only in water, then that would take place as well. But this is really like one of my beaker of stuff questions where I'm going to circle everything I have. I'm fairly certain there's a water down here on the table, like as low on the table as it can go. There's also a water roughly about up here on the table, and acetic acid is somewhere about in the middle, give or take. You guys find all of those? Now, hypothetically, let's remove the hydroxide from the equation. Say there is no hydroxide. Can this acetic acid react with water? Sure, but like 1% of the time. However, put a base nearby, and acetic acid says, screw you, water, I don't need to worry about you anymore. I want to get rid of my proton, because really, this guy right here wants to get rid of his proton. And he's trying to pawn it off on water up here. This is like me and Daniel with the pen. I wanted to get rid of the pen. But does water really want the proton either? Well, no, so it just passes it right back. But let's say that there's not just water available. Let's say that there's hydroxide available. Well, now I want to get rid of my pen or my hot potato, my proton. And now there's a hydroxide nearby, and I give it to Darian. And Darian says, sweet, I've actually really been looking for a proton. Because you know what? This guy down here really wants one. Okay. So in terms of us writing our reaction, it's going to look something like this then. Your CH3COOH, which was aqueous, is really not going to react with water because it's found somebody better. And my Taylor Swift analogies are really good here. It broke up with water, and it wants to get back together with water, but hey, it found a new boyfriend somewhere over there, right? And hydroxide is so much more attractive. Hydroxide is taking me to the movies and pays for hydroxide will take my hydrogen from me and turn into water. And finally, what will the other thing be? It'll have to be CH3COO negative. Now here's the question. If this thing's going to be at equilibrium, is it going to be more than half the time or less than half the time? More than half. Now, I don't actually have a way for you right now of knowing how much more. We'll get to that. But right now, I can say that this happens at least more than 50% because of the trajectory there. So I'm expecting to have a lot of this stuff here. Will there be a little bit here? Yeah, a little bit, but not that much. Okay. Last thing, I want to make sure we're good at our terminology then. This would be an acid because it gave away its proton. This would be a base. This guy over here would be the conjugate base for this acid. Because this one and this one are pairs with each other. And this water right here would be the conjugate acid for this base. That's the terminology I want to make sure I'm doing a good job of explaining today. Because this proton right here, there's a hydrogen sitting right here, right? Why don't I even erase it? I'll put it in another color. Just to help illustrate it. CH3COO. And then I'll make the proton green. What's really happening here is this guy right here. Oh, apparently I can't pick it up. Oh, what did I do? No, no, no. Okay, well, apparently I can't pick it up like I do with my old program. It sucks. So imagine, I guess, right? This hydrogen is leaving this guy and attaching itself to there. And what have you made? Well, now you've made this HCO3 minus and this water. But once in a while, this hydrogen is going to go right back to this guy. And then back to this guy. And you guys get what I'm saying here? And it's just going to keep hopping back and forth between the two. But where are you going to find it more likely to be? Is it more likely to be on this one or on this one? It's more likely to be in this stage here where the proton is actually on the water and this guy's there. And I realized that that's more because I said it was more than 50%. So the terminology we would use then is we would say this one has products favored. You guys able to follow that? Let's try another one. I think I only have one more example left. So I'm going to sit back over here. The board is being glitchy. Test it from here. Okay, so the next one here, ammonium nitrate fertilizer is produced by reacting ammonia with nitric acid. Let's try to write our equation. So again, I'm going to start by writing out some of the stuff I have. It says I have aqueous ammonia, so I must have NH3. If it's aqueous, though, I have to consider that water is also a possible reactant. And finally, it said I had nitric acid, so HNO3. That's the stuff I have to work with. Since nothing here is ionic, I'm not going to worry about dissociating anything. But if there was an ionic compound, I would dissociate it. So now I'm going to consider my table. So again, imagine this is your table here with like the page break in the middle. Water is about here and very, very lowest. Where is HNO3? That's one of the strong ones, right? So HNO3 is up here. Where is NH3? Is it down in this bottom corner somewhere? Or no, it'd be on, yeah, it'd be on this side right here. Is it roughly about there? Give or take. Okay. So here's where we have to consider that could this nitric acid react with water? Yeah, it could. Would this nitric acid love to give its proton away to water? Sure, but you know what? It found somebody even better. Right? Rather than it giving its proton to water, it could give its proton down here to the ammonia. So this would be the most spontaneous reaction. And so what's going to happen here then is your HNO3 will react with the NH3 to form. And then here's where the data booklet actually is kind of useful. If you're not really sure what it's going to form, then look at this. The HNO3 is going to turn into whatever was sitting here. So if you're really stuck, the HNO3 will turn into just good old NO3 negative. And if you're stuck on trying to figure out what this guy is going to turn into, then just make it go the other way. Do you guys see how this is almost the exact same as the electrochem unit? So NH3 will actually turn into NH4. One more thing. Because of the raw distance between these guys right here, I'm going to make a hypothesis. I'm actually not going to put a double-sided arrow because it is so far away that I bet you if it does go back at equilibrium, we're probably talking like 0.1% maybe, right? And that's just due to the raw distance apart. If you had someone here and here apart, yeah, maybe that's going to be like most of the time, but maybe it's not necessarily needing to be like, you know, a single arrow, but I bet you we can get away with a single arrow here. I can still label everything though. This is my acid who gave its proton to this base. The conjugate base of this acid is that one right there. And the conjugate acid of this base, those guys are the pairs. However, when this proton goes from here to here, I don't believe it's coming back again, just due to the complete distance between them. You don't actually have a way of knowing that, by the way. Okay, not without having a little bit of math behind it. So, I mean, the general idea, I guess, would be as soon as it starts getting far enough apart, then you can maybe take an assumption and say, okay, it's probably not needing to be a double-sided arrow. Okay, that's more or less the basics of my lesson today. You guys have any questions so far? Okay, I'm just gonna look through the slides I skipped, see if there's anything else relevant I should talk about. Let's see, this one here. Overall, yeah, basically the concept is the reaction should be from your strongest acid to your strongest base. Okay. If I go back to this slide right here for a second, like the one I just did, could this guy have reacted with water? Yeah, it could have. But just like in redox, what's more likely to happen is this guy will react with the furthest guy down here. Okay. If this thing didn't occur, then sure, then this guy would have reacted with water. Okay, what else did I miss here? This is what I was talking about as well. If it's in a downhill trajectory, more than 50. If it's in an uphill trajectory, it can still happen. It's just less than 50. That's all. This just gives you some written notes as to what to do. I think I've kind of covered that. This slide right here is kind of useful. If you ever have an ionic compound, I did discuss this briefly. You should dissociate your ionic compounds. Okay? If you have an ionic oxide, ionic oxides will actually produce hydroxides. I don't know that I've ever seen this come up. I guess the reason why is that this thing right here, calcium and oxygen, what'll actually happen is this oxygen will find a water. You know how like if you dissociate this, it'll give you calcium 2+ and oxygen 2-. If you ever have one of those, the oxygen 2- would find itself a water, and what would happen is it would rip a hydrogen off of the water, and you'd actually getting 2 different OH minuses. So if this ever comes up, and I don't think I've ever seen this, but if you ever have an oxide, you actually have hydroxides. Did that make sense what I said there, or should I explain that better? So if you ever see, like say CaO, here's what's really occurring. It's going to dissociate into Ca2+ and O2-, but this O2- is not very stable at all. You probably have never even seen me write an O2- before. Like it's not something we do a whole lot of. Because what's going to actually happen, nope, that's not what I wanted. Let's try this one. There you go. Okay. What's going to happen is this thing right here is going to react with some water, and then a hydrogen is going to pop off of this water right here. And what you'll end up getting is this guy right here will have an extra hydrogen, and so it'll be OH-, and this guy right here will also become OH-, and so you'll just make yourself a lot of base. So any ionic oxides are actually basic, if it comes up. Strong acids, you can write them as H3O+ if you'd like. That's also a possibility. Yeah, really, these ones right here, you'll notice that like if you have HF, you're just looking for HF. If you have HCO3, you're just looking for HCO3. So I think I've kind of covered what you need from there. And yeah, other than that, if this is just the terminology I mentioned, strong acids hold their protons weakly. It seems weird because you'd think strong would be good at keeping something, but this is hot potato. So if you're strong at something, you want to get rid of it. So strong things, if your acids get rid of protons, strong bases though, want protons. Wait, I think I've covered everything. Any questions? So here's where we go. We have 2 lessons left, and we are done the year, not only the unit. So a couple things for you guys to start working on then. I don't have many things in this unit for us to do. I've kind of cut it back. So we just did the 1 lab. So you probably should work on that first and foremost. There's only going to be 1 assignment, and you probably can start working on most of that assignment now. There'll be a few things here that I haven't covered, but I've covered the biggest parts of the unit. Why don't we have a work day tomorrow, because it's Friday, and then Monday, rather than having the quiz Monday, let's do the quiz Tuesday. I want to give you 1 more lesson before you do the quiz, just because I think it'll help. So, sound good? So then I think the plan next week is lesson Monday, quiz Tuesday, lesson Wednesday. Next week, Wednesday, I'll have covered all of chemistry. Yeah, that's cool. Eh? Okay. Yeah, you guys have about 20 minutes, 15 minutes left today, so I guess work on whatever you need to finish. I guess actually one last thought. Don't forget to finish up that essay, the research paper from the organic unit as well. Yeah, I haven't forgot about that. I really do think you guys should try that. Well, you guys already probably did 2 full days of research on it, so. Or did you just surf the internet the whole time and not do anything? I know. Okay. I had a day set aside for us to do a lab. Why don't I book the laptops that day so I can give you one more day with computers for that? Okay. Okay.